So let's start. The recording has been started. And all right. Again, is everybody able to hear me clearly, or is there any break in the voice? Is my voice coming through clearly? Great, great. All right, all right. So I hope you had a great time during vacations and also got some time to work on those problems. All right. So I think I have already discussed the basics of Linux command line. Is that right? Yes, Mahesh. I can see your response to the questions. It will be great if you use the questions window instead of the. I'm not sure if you can use the questions window, Mahesh, because you are organizer. All right. So Mahesh, I'll have to check whether the you check the assignments, and if I mean, once you submit, you just have to inform me that you are done with the questions, and then I can take a look at it. All right? Okay, okay. So I'll take a look at it because I get too many notifications from the system saying some person has submitted this and all that. That's why I generally am not able to get the alert. So yeah, I'll take a look at it after the session. All right? Great, great. All right. Okay, so today we are going to discuss a very important aspect of MapReduce. And before, all right, we have everybody. Okay. All right. So before we start discussion on the questions which I have given you in the last session, I would like to go through the the one very important way of getting the MapReduce work done via streaming job. Okay, so the streaming job is something which gives you a very quick way of very quick as well as a very flexible way of getting the MapReduce work done. All right, all right. So to be honest with you, when I started with Hadoop, even though I'm a good Java developer, I started most of the work on recommendation and a couple of more projects using the Hadoop streaming. Okay, so Hadoop streaming is basically a a MapReduce library, which you can think of as if it's somebody who has written the MapReduce already. And what does this MapReduce do is instead of writing its own logic to give out key values, it takes your program, it passes the input through your program, and then it uses your program to to pick up the key and value. All right, I'll describe to you how does it work. All right, I'm sorry, my screen was not being shown. All right, now is it? Yeah, now were you able to see it? Okay, okay, yeah, great. Thank you for letting me know. All right, because I think these guys have upgraded this GoToWebinar version, and it does not start showing the screen when I start the meeting. All right, I'll keep that in mind. All right, so coming back to it again. So as we discussed in the previous session, when we are going with MapReduce, so you write your program called mapper and another program called reducer, and you give to the framework that hey, here is my mapper and here is my reducer, and then using mapper the key selection of the key happens for Hadoop, and using reducer how the values for each key gets aggregated, that is decided. Okay, so effectively to get your work done, you only need to specify the key value as part of mapper and a way, a logic or a program to convert multiple values into a single value. Correct? Now, not everybody is a Java programmer. Also, writing the code in Java restricts us from using our own binary. Okay? Imagine that you have a legacy code and you need to get that legacy code executed, and this legacy code will convert the input data. This legacy code will convert the input data into key value pair. Correct? Now in MapReduce we cannot afford to convert this legacy code into Java. Right? Now third point is that in Java, it takes a lot of time to basically write code and test it out. Correct? And it's too much of too. It's though it's powerful, but it takes a lot of effort. It takes considerably more effort than writing using a shell programming or some other language. All right, because Java is like strongly typed language and you have to compile it and then run it. That's why. All right, so these are the three reasons why Java MapReduce were little uh, not I mean they needed a library where people can start working using any programming language, and that's where comes the Hadoop streaming. In Hadoop streaming library makes it possible to use any binary as mapper and reducer. Okay, now this the what is again, so somebody wrote code in Java called Hadoop streaming, and this is basically a MapReduce program which takes your binary of program, binary as in any program, like ls is a program which is a command line, sort is a command line program. So all of those things can be used here. Or let's say that you are into a brokerage firm and there is some legacy code to convert stock price from one currency to another. You want to use that as a mapper. All right. Also, please do not confuse the Hadoop streaming with the stream processing engines. Here, streaming means passing data through a program. Like the way we pass the data through graph, like the way we pass data through sort command. While I was giving you demo last time, where we used sort command in the pipeline. So there also we are doing the sort command. And you remember SED? What does it mean by SED? SED is a command in Unix and which basically you can edit the input data or change the input data coming to it and save it in some other file. So SED stands for stream editing. And from here itself, the this whole streaming mechanism, you will see the streaming terminology being used at three places. One, using the stream editing like Hadoop streaming, or there'll be something called pig streaming, and we'll also talk about streaming in the context of Hive. Okay, where we take the data, we take the data and we take the data, pass through the data via a program. And this program might do things like only let few lines go into the output or translate the input data into something else. So that is one uh, one way the streaming terminology is used. Other is stream processing. What does it mean by stream processing? You have terabytes of data or data coming at a very fast pace, and you want to do some processing of the incoming data. Like and like for example, like for example, your users are visiting the website and you want to count how many web users are there on your website, the velocity part of the big data definition. So that's another way the term streaming is used. The third way the term streaming is used is streaming the video. Like for example, when you watch YouTube or you watch movie via Netflix, you're basically streaming the video, or the server is streaming the video to you. Okay, so that's the meaning of the word streaming. All right. So now, question to you is, there'll be a question from your side to me is that, okay, fine, this library lets us use any binary, any program as mapper, and any program as reducer, any code, any existing uh, executable, you can use it as mapper and reducer. But how would this program understand that what is the key and how would that communication happen, right? So that's a very important aspect. So streaming job says that I'm okay with any mapper in the command line as long as your mapper is taking data from standard input and giving the data to standard output. Also, your program, whatever is your program, it needs to give me whatever is your mapper program needs to give me the key and the value separated by tab. All right. So Hadoop streaming says that your program, if you want to use some program as mapper, you can specify on the command line, but your program should give me the data, the key and the value separated by tab. Otherwise, how would I know that which one is key and which one is value? Because I'm reading line by line from your program. That's what Hadoop streaming says. Hadoop streaming basically reads a record from an input split, reads a record from the HDFS or HDFS blocks. Okay, we will talk about input split later. So Hadoop reads data from HDFS blocks, converts it into into a logical form like record by record, and for each record it's going to call Hadoop streaming library. And when Hadoop streaming library gets called, it's going to call your executable program. Okay, so for each record it's going to feed that record to your executable in the standard input, line by line. And now, once your program receives the standard input, your program will have to do something with it, right? And that something is giving out key and value in the form of key separated by value by a tab. Okay, key, tab, value. All right. Now, there might be a question from you is, what if my program doesn't? Okay. What if your program does not give the tab in the output? It just says XYZ and that's all. So whatever, if the tab is not appearing in the output of the program, then Hadoop streaming will take the whole line as the key. If there are multiple tabs, in that case, it will take the key before the first tab. All right. So that's how it behaves. So I think a better way would be to give you a quick demo, and that will give you a bigger confidence. All right. So, so the screen is off and on. That's what Midili is saying. Is that true? All right. Any questions at this point? I have a question from Mahesh. Mahesh is saying that do you have a sequence diagram to show the show the sequence of interaction with the numbers? All right. Let me try to do that. All right. Midili, it seems to be stable for everyone. All right. Maybe there's a fluctuation in the in your connectivity somewhere. All right, let me try to first demo you and then we will talk about it, okay? All right, so all right, let me try to give a demo. So let's go through this command once and then we will, okay? What does this command means and how does it matter? All right, is my screen visible to you? Great. All right, so let's try to understand this and then I'll give you a quick sequence diagram and that will help you. All right, so this will be your probably the first quick program in with MapReduce. Okay, so you can see that Hadoop jar and this jar. So this is the Hadoop streaming code. All right, generally If you are a Java programmer, you will be creating your own jar file where you will say Hadoop jar, my program.jar, or whatever is your program name, and then you will execute that. Now this will execute any bundle of code written in Java, okay, on Hadoop. Okay, we will go into details of how to create a program in Java, so that we can specify mapper and reducer in Java. Okay, so right now let's go with Hadoop streaming. So this library is something which was created by somebody in Hadoop's team after Hadoop was created. Now the rest of the things are arguments to these arguments will be fed to this program. These arguments will be made available by Hadoop to this Hadoop streaming. Okay, so the first argument is minus input, and this is the data folder. This is the data folder in which we are feeding as input to our mapper reducer. Okay, next is this is the output folder where we want the output to be. Now who is going to convert the input line into key and value? Here is the culprit. This particular line says that my mapper is SED. Okay, my mapper is SED, and then the argument to SED is substitute. This is the argument to SED. It says that it's a substitute space with new line. Okay, and this is the reducer. All right, this is the reducer. Now going ahead a bit. So where is our console? Is everybody able to log in here on the console? Yes, Yaswant. We will be discussing the previous session assignment after this. Okay. Yes. The input. His next question is the input can be database. The input can be database also, right? In that case, how will this work? We will talk about this. Okay. We'll talk about this. This is a good question. Okay, his question is, can you explain the mapper part again? Okay, let me try to explain. What does this command means to you? All right, that's a very important aspect. So, what does this command say? Whatever input I get, I will replace space with new line. Let me try to show you. Okay, let me try to show you, and let me first get out of here. Okay, let me try to show you here. So if I say SED, okay, and I say substitute space with new line, okay, it says substitute the space line, the something which is between the first two slashes with something which is between the last two slashes. Okay. Now if you can see, if I say Sandeep Giri, you can see it has immediately translated into Sandeep new line Giri. Okay, A space B, it has substituted it into this. Okay, if I say twice, there'll be a gap between the two because there'll be two new lines. All right. So anything you feed it, whether it's in terms of the standard input like the way we typed, or we pipe to it. If we pipe to it also, then we get these two lines. Correct? All right. All right. Another question is, what does this G means here? G means globally. If there are 10 lines, 10 spaces, then also it will work fine. Okay. You can see that. If I do not specify G, it only replaces the first space with the new line. So that's about a command called SED. SED means SED is just a way of manipulating the input line into the form whatever we want. Okay. Now we could have said here uh, something like this, substitute space with tab 1 and then new line. Okay. All right. Now, this SED is basically going to give out one word per line. It's going to give out one word per line. Correct? Is that agreeable to everyone? It's going to replace space with new line, and effectively it means it'll generate one word per line. Okay? Uh, Great. Okay. Now, so this part is clear to everyone, and these two parts. So this is our input folder, this is our output folder, and this last slash is so that we can have multi-line command. If you want to execute something in multi-line, you just put slashes instead of you do either you take everything into the single line like this, okay, either like this or okay like this. So either you take in this form or you take, all right, good. Now, second part is that this is basically unique minus C. What it does is whatever is the input, it counts the frequency of words in it. Okay, it basically finds the unique words frequency in the output or unique lines frequency in the input given to unique. Okay. Mm, but the only condition of unique is that the whatever you do, you give it the data in the ordered format. For example, I'll show you a slash n b slash n b. Okay. Uh, uh, Let me a b c a b. Okay. You see this? Now, if I feed this to unique minus c, what happens is saying uh, A has occurred once, B and C. But if you sort the data before giving it to unique, it will be able to count it correctly. Okay, so all unique does is given the input data, it keeps on reading the word and counting it counting its occurrences as long as it's continuously same word. Okay, if let's see, so if we sorted AABBC and these have come out good, I mean they have come out in order, then unique works fine. All right, then unique is able to count it. But if you don't sort the input, it doesn't work correctly. All right, that's its definition and that's how it works. Good. So these are the two commands. One is SED and other is unique. All right, Abhay is saying the commands. This command says no such file or directory. Let me try. So his point is that this command says no such file or directory. Okay, let me see what is done. For me, it's working fine. You can see that I've just copy pasted it. The question from Midli is that these commands only matches for word counts, right? Yes. So SED, no, these are the general command of Unix, which we are trying to exploit in order to do some MapReduce work, such as word count. Now, question from Mahesh is, Mapper has to give key value pairs, but SED is only giving one key. How does it work? If it is giving one key, it will assume value to be null. Okay? It will assume the value to be blank. Now, a question from Mahesh is that can you give a real life example? How can we use this streaming job? All right, just give me a second. As a note, we will take example of grep. Okay, we'll take an example of grep. Okay, so let's go back to this one. Here, we will be taking this data as the input folder. Again, this has to be in HDFS. Okay, so the file is existing. Okay, all right. All right, let me just take this example and try to run through it. So it says the input command not found, and the reason is there has to be a slash here. All right. Okay, looks like it has done some work, although it gave error on the first attempt. So a particular block has been removed. Okay, so I'm checking in the HDFS, is it created or not? Yes, you can see that it has clearly done the, okay, you can see that it has created part 00 and part 11, and it has generated the word count. Now you see that because of the double quote and these punctuation marks and the spelling, I mean the casing, there are a lot of differences in it. You can see. So the command has worked well. Now our next target is to make this output look better. What can we do? What other things can we do in order to make it look good? Anyone? Yeah. What are the things that we do in order to make it look good? Because you can see that it forward has come here try so many times. Okay, Mahesh says that output should be sorted. Okay, all right. Replace special characters with space. Okay, we'll do that, Mamta. All right, we can use group by. Okay, group by what? Number of counts, which are the words which occurred 17 times. Okay, okay. So how will we reach? So there are three things. One is replace special characters. Second is sort this output. And third is use group by. Group by as in instead of using MapReduce, you want to use group by, or you're saying that group them by number of counts. Okay, okay. That's what we are doing actually. Okay, so his group, her point was to we can use group by. Okay, all right. So that's what is happening behind the screen. So question that might be bothering. How is it working? To how exactly is it working? So let's take a look at this diagram. All right. So in case of MapReduce, Mapper is going to execute the Hadoop streaming's mapper. There'll be a code inside Hadoop streaming job. Is going to execute our mapper, and that mapper is going to convert the input line into one word per line, like this. You see that? Like this. Okay. Now because this is one word per line. Okay. It's the first one is considered as the key, and the value is null. And Hadoop streaming is completely okay if the value is null. All right. So it's going to break down the each line into one word per line, and then Hadoop will sort that data. And once it has sorted the data, it might have grouped this these keys. Hadoop streaming ungroups the data, creates the sorted file. So Hadoop streaming uses Hadoop only as a sorting machine, not as a grouping machine. It does if because Hadoop will be grouping this data by the key, and Hadoop streaming interestingly will ungroup the data. Okay, ungroup the data such that the data is only ordered, not grouped. Okay, so Hadoop streaming uses MapReduce using using MapReduce. It gets the data sorted, and then for each of the line, it executes for the output data after sorting. So at this point, the data has been sorted by Hadoop. Okay, sorted and grouped. The streaming job would convert this into only sorted, not grouped. Okay, and then this data which is sorted here will be fed to the unique minus c, which is our reducer. And what does unique minus c does? It basically counts the occurrences of a word if they are nearby. Okay, in a sorted data, the unique command can find the unique words, or unique minus c can find the counts of unique words. Is it clear to everyone? So Abhay's question is, if Hadoop streaming does this for me, what should my mapper do? MapReduce do? Okay, so Mahesh, this one is for a single reducer. We'll talk about the multiple reducer in the next diagram. Okay, so his question is this: if Hadoop streaming is doing this for me, then what does my MapReduce do? Your MapReduce does everything. Okay, so here SCD command is your command. In place of SCD command, you could use something else. In place of SCD command, you could have used some other command or some other program. Instead of SCD, you could have used your own Python program, or you could have used a bash script. You could have used, if you are on Windows, you could have used any exe instead of SCD and unique. Okay, can you display the same with a program written in some other language like Python? Okay, just let me try to do it. Another question is, does the usage of std out and std in comes with any limitation? No, not because any communication with various processes can very well happen over std out and std in. All right. All right, we will show you this part in a minute. Okay, this part in a minute, and if possible, we'll try to do it next time, because okay, I'll have to write it on prompter. Does the usage of okay? Good, good. So, all right, let me just quickly go through, let me try to answer this particular question. If Hadoop streaming is doing this for me, what should my mapper do? Mapper and reducer. Your mapper and reducer are somebody who is taking the main decisions. Okay. All right. Let's take a case that there is this input file and it has got many words. It has got many words like this. Okay. So for each of the input, this is our input file, by the way. This is our input file. Okay. And you can imagine that this input file is made up of many blocks. Okay. These are the many blocks we have drawn here. And then for each of these input blocks, so I can say this is our block. Okay. For each of the input block, our mapper reducer is going to get executed. This is our Hadoop streaming mapper. So inside Hadoop streaming, there is a mapper which executes this stuff for you. Okay. Here. Okay. After this, after the this is a block. Okay. This is a block. After the data is broken down into blocks, so block is being fed to the Hadoop streaming mapper, and Hadoop streaming mapper is calling our library. Okay, this is calling our input, or we can say our binary. Okay, and whatever our binary gives out, that one will go to the Hadoop. Okay, that one will go to Hadoop streaming, and then it will go to, all right. So the data from uh, or you can say, yeah, here the data from input file is being read by Hadoop to give us one input split at a time. Now, for each line or each record of the input data, Hadoop streaming mapper is going to get executed. And that Hadoop streaming mapper is basically calling our binary to get the actual work done. And when the actual work is done, then that work is being given back to Hadoop. Okay? And that work is nothing but uh, generating key value pairs. While this binary gives tab separated A tab B and B tab C and so on, this binary, while this one prepares proper key value pairs needed by Hadoop Java library. Does it make sense to you? No? Is it clear to everyone? Looks like not clear. So So generally, what was happening earlier was when we were telling that Hadoop streaming is, sorry, the MapReduce is going to do your work, Mapper is going to do the job. So Hadoop calls Hadoop streaming's mapper. Hadoop streaming's mapper forwards that work to our binary and again takes up the output given by our binary and gives it to Hadoop. Okay, so Hadoop streaming mapper is like a proxy mapper. It's like sitting here as a proxy. It's being forwarding everything to us. All right. Right? So this is what is happening. So our program effectively will convert the input line into one word per line because of SED, and then the output goes to Hadoop. Output goes to Hadoop. Hadoop sorts it and gives it to unique. Unique basically counts number of times each word has occurred. All right. Okay. Now the next stage is what if there are multiple blocks. If there are multiple blocks, again, for each block, this is there will be so for each block, our program is being called, and our after our program gets called, the data will be gathered, and again the shuffling would happen. Okay, shuffling would happen such that one key same key is only on one node, not on different node. For example, assay is on the same node, not on different machines. Okay, so the data is being converted into key value, and key value are in the form of key tab value. Okay, that are being given by our mapper to Hadoop streaming, and Hadoop streaming is feeding that data to Hadoop, and Hadoop is sorting it. And then, in case there are multiple reducers, in those cases, it can basically split the number of keys to different nodes. Okay, so that's the job of Hadoop to split the data onto to split the key values into multiple reducers. Okay. Mitli's question is, isn't that reducer grouping the sorted data? Okay. You mentioned it's ungrouping the sorted data. Okay. So I'll come back to it again. It's a very good question. Let me try to explain. Yes, I was waiting for this particular part. Yeah. Okay. Isn't that reducer grouping the sorted data? Isn't that reducer grouping the sorted data? Yes. It's the reducer that is grouping the sorted data. But Interestingly, interestingly, Hadoop internally groups the data for you. Okay, but if you see, the unique command is getting ungrouped data in input. Who is how the grouped data? So again, yes, I'll come back to the example, Abhay. Okay, again, just like we talked about this mechanism while we so let's say this is coming from us. Let's say we gave A, B, C, D, C, A, B, D. Okay, this is the output we gave to who? To Hadoop streaming. Okay. So let me try to do this diagram. So this is coming like this. Okay. It goes to, this is Hadoop. Okay. This goes to Hadoop. Okay. And ABC, ABD, and this goes to Hadoop. Then it goes to, from Hadoop, it goes to Hadoop does the sorting, will do the sorting for you. Okay. Okay. Hadoop does the sorting and grouping for you. Hadoop will do something of this sort. Okay. Hadoop will bring all the values together. Or you can, let me, how should I okay, let me try to describe it like A, comma, 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 comma. Okay. Because the values are blank. Okay. So the values are being grouped here by Hadoop. Or how should I describe this? Yeah. So Hadoop is basically grouping the data in this form. Let's say space or null, comma, null, comma, null. Okay, null, comma, null. Because here it's basically the input to Hadoop is null, 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 null. Okay, like this. Okay, because our program did not give the value, therefore Hadoop streaming took it as null and give it to Hadoop, and then Hadoop is converting into A space null comma null, and B is again twice, and there will be no B here, and C is going to be only null, and D is going to be null. Okay, this is what Hadoop is going to generate for you. Why is there a null? Because our SED program only generated single word per line. It did not give word tab value. There was no tab and value, and therefore it's considering that value as null. Okay. Now Hadoop given this input, Hadoop grouped the data for you. Okay, and once it is grouped, it's again given to Hadoop streaming. This is again given to this is again given to Hadoop streaming. Okay, so Hadoop streaming is, I'll say, Hadoop streaming, and Hadoop streaming is going to convert this data into this form. Is going to convert this data. Right. Sorry for bad graphics. Hadoop streaming is going to convert it back into A null, B null, and again B null, C null, D null. Okay, that is good. All right. All right. Next is that we could, this will go to unique command. This will go to unique command, and the output we will get is A, sorry, 2A, 2B, and 1C, 1D. Good? All right. Or if you want me to draw a picture of our map, I can do that also. Okay, let me take it further. Yeah. All right. I think it should be clear now. All right. Now, what's happening in this whole process of word counting? Okay. I will again say SED here instead of. So SED gave us one word per line. Okay. A, B, C, A, B, D. And Hadoop streaming converted internally into A null, B null, C null, and so on, because Hadoop wants some key to be present, okay, some value to be present for each key. And then Hadoop sorted and grouped. Hadoop sorted it and grouped it. Okay. And once that is done, again the call goes to Hadoop streaming reducer, and Hadoop streaming reducer converts it, unfurls it. Okay, so you can see that grouping is happening, ungrouping is happening after grouping has happened. Okay, so that's like an overhead, but that's very minor, because grouping assorted data is very straightforward. You keep on going from top to bottom, like here. You keep on going from here. As long as it's the same key, you keep on aggregating. Otherwise, you start with a new one. Okay. All right. Is this clear to everyone what's going on here? No? Did I confuse you? Mahesh's question is, all right. Mahesh's question is, it is adding a lot of overhead to the process. And how does streamer know how to convert it or split it? So this command is something you can change. This as well as this command. This is something which is yours. Okay. So your question, I did not get, Mahesh. So it's adding a lot of overhead to the process. Is that your question? All right. Okay. So here, as you can see that Hadoop data grouping and then Hadoop streaming had to do ungrouping. Why? Because Hadoop has been designed that way only. Hadoop has been designed such that it will group all the values for each key after sorting it. And Hadoop streaming will do that. Now his question is, how does streamer know why it needs to add null and how to split that again? Okay, so Hadoop streaming, that's a kind of understanding. When we do Hadoop streaming, we are going to give it one record per line. Okay, and the key and the values will be separated by tab. If we had given here, if we had given something like this here, it could have, or here you can say, I'll try to write tab. If I'm pressing tab, it's going to the next line, so I'll just mark it like a tab. So if we had a tab here, it could have been easier. Okay, it could have been easier. All right. So we had it put tab here, it could have just taken a tab and one, and then one could have been key. Then it would have taken it like one here, and so on. Okay, does it make sense to you? Since we did not give a tab and we did not provide any value, it's taking value as null for each of these keys. All right? Good? All right. Now moving on. It'll be difficult to take a break. Yashwant is asking for a break. You guys want a break right now? Yes. This is something I want to talk about after this thing. Does anybody else want a break right now? All right. All right. Let's take a break in like few minutes. Okay, Ashwant. I think okay. We'll just stay with our usual timing. All right. So there are two things I had to do. One is I have to take a real life example on where streaming is used. Okay. So I'll give you the most real life one, which I have used multiple times. Okay. So the first one is, let us take a case of finding. Okay. Let me just set up the scenario. Okay. So you are having this website, say a e-commerce website. This website is running day in, day out. And when users are visiting your website, a lot of errors are occurring in the background. And what you want is, you want to look out for a pattern in the log messages, okay? And then figure out how many errors have occurred in the whole day. Okay, what you want to do is, every day you want to run this job which finds out how many errors have occurred in the whole day. Okay, so what do you do in such case? How do you, how do you, it's a very simple task. It's a very simple task of finding all those lines where error message has occurred. You want to find out all those places where the error has occurred in the file. And also note that this there could be hundreds of files. If you have a very popular web server, there could be hundreds of web server answering to the questions, okay, answering to the queries of the users. So there are hundreds of web servers running, and all of them generating the logs, error logs, as well as information logs, as well as debug logs. Now you have to find out quickly where is a particular error message occur, where at how many places did a particular error message occur. In those cases, you could simply use grep as mapper. Okay, so you could simply use graph as mapper. All right, let me, okay, that's another question from Mahesh. We'll talk about it. So we'll use graph as mapper. Let's say these logs are this file which we have been working on since morning. Let's say this is the same file. Okay, it's the same data which contains log. And And what we want to do is, this is our input data. These are log messages of various servers. This folder contains the log files from all the servers. Now, okay, and we say it error out. Okay, and here we say find out all those lines, or let's say how many times this word called error has occurred in the output. So we want to count here how many times error has occurred in in the files in this folder. Okay, so we are basically using grep and unique minus c to count it. Okay, or we could just say w word count. Okay, let's try to run it. Okay, so it has created this error output, Hadoop fs minus ls. And what do we want to do? We want to see what is there inside Hadoop fs minus cat and this file. Okay, so it says that these many characters, these many words, and these many lines. So there are 93 lines. Okay, so effectively there are 93 lines which contain the keyword called error. Okay, and in case you do not want to set the reducers, you are completely free to do so. In that case, the output of a mapper will directly go into the HDFS. You can see that the output of the mapper, it, it is trying to execute. Maybe some of the machines are down. I've not checked my cluster. Okay, so here you will see that the lines, you can see that these are the lines which contain a word called error. You can see error here, here, inside the words. You can see that. All right. So this is a real use case every day. So what we used to do is we used to analyze what kind of errors are occurring. So as part of this program, as part of the mapper, we will convert the input line such that the key is error message and value is maybe nothing. Okay, key is the error message, exact error message. So we were able to count how many times particular error has occurred in production, so that we can diagnose and we can make that an agenda of the whole team that these are the most important errors that occur in production. All right, was I able to give you a good example? So we were able to do quickly the churning of the data rather than sitting back and trying to code it in a Java kind of language, because these programs do not always need a Java kind of environment, because these are very quick works and you should be able to do it quickly rather than waiting for somebody, rather than waiting for writing the Java program, compiling it, uploading it. In case there's an error, we again do it. So most of the work can be actually done using tools like Unix, tools like Python, okay, along with Hadoop streaming, and that should be good. All right, all right, good. Now, next question from Mahesh is, why do we have multiple reducers? Can somebody answer it? I like to see your answers. Yes. Abhay, Bishwa, Lakshmi, Mahesh, Mamta, Midli, Yashwant. Yeah. Anybody? Why do we have multiple reducers? Anyone? So why do we have multiple reducers? Anyone? Yes. Okay. Let me try to explain. Why do we have multiple reducers? Okay. The answer is very simple. The answer is that lot of times in our reducer case, right now we did not have a heavy workload in reducers, but lot of times reducers are under the huge load when there are a lot of values to be combined, and that logic of combining all the values for a key is complex. Imagine that you have to compute the sum of squares, the square root of sum of the squares of all the values for each key. Okay, you want to do that. You want to compute the square root of sum of squares of all the values for each key. Now, in that case, the very reducer will be heavily loaded, because by default there is a single reducer. And why there is a single reducer? Because all the keys and the values go to the single reducer. Okay, because multiple keys, sorry, all the values for the keys have to be passed through a single reducer. It cannot happen that some of the values went to one reducer and some of the values went to some other reducer. Here we want all the values for a key must go to a same reducer. Okay, otherwise the logic of, say, summation, where half of the values are on one machine and half of the machine values of a key are on another machine, the summation or any aggregation will give us wrong results. Okay, so I hope that is clear to you now, Mahesh. Yeah, did it make sense? To reduce the workload of single reducer. The question is, how is it achieved? All you need to do is you need to just say how many reducer you want here. Okay? How many number of reducer you want, you can mention it on the command line. Question from him is that MapReduce paradigm of Hadoop is that it sends all the keys are sent to one node. No, not all the keys. Okay? It's the identical keys. Look at this, all the values with the same key get executed on a single reducer. All right. So if you have a million keys, and for each key is repeated 20 times or 50 times. Okay. If you have a million keys and each key is repeated, say, 50 times, which means total 50 key value pairs you have right now. Okay, total 50 million key value pairs you have right now. So at most, reducer, okay, so the number of total reducers can be at most a million, because it doesn't make sense, right? Also, I think I should give you a couple of more ideas. One is, if number of reducers are greater than number of unique keys, okay, the sum of the reducers will not get any work to do. Okay. Why? Because let's say if you have two unique keys and three reducers, okay? One reducer will be empty. All right. So he's referring to a slide which I discussed in last class. Okay. So right now, yeah. So the question here from Mahesh is how keys are split for reducer. Don't worry, we will talk about it as we go ahead. Okay. So some of the key, basically, some of the keys go to one reducer, some of the keys go to another reducer. Okay, for their work. All right. This diagram should help you. Yeah, this diagram. This diagram. Okay. So some of the keys are kept in one bucket, some of the keys are kept in one bucket, and that logic is based on hash code. Okay, so for each key, a hash code is generated. Hash code is like could be like sum up all the letters in a word, and then divide by 30, and whatever is the remainder, that becomes the hash code. So that kind of thing. All right. So this division, exact division, is if we will go into its detail very soon. All right. All right. So the next agenda is we improve our script, the word count script, such that we are able to remove the special characters, and we'll talk about it after the break. All right. Let's take a break for 10 minutes. Back by 8:43 a.m. IST. All right. Is everyone back? Can we start now? Hi. Is it? Can we start now? Is everyone back? Abhay, Biswa, Lakshmi, Mahesh, Mamta, Midli, Yashwant, and Mahesh. Hi. Are you able to hear me clearly? Where are the questions? I can't see the questions window. Oh, here. Good, 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 good. Oh. Actually, you guys were answering, and I could not see the questions window. It has hidden under the under the hood. All right. Great, great. All right. I think these are very good answers. I think I should write it here. Very good answers. I think I should. Okay. Okay. So Mahesh's answer is to spread the work on multiple machines. Okay, that's good. Biswa's answer is to get the work done parallelly. That's correct. Midley's answer is to reduce the workload. And then Abhay's answer is split reduce job across multiple reducers and making fast. Yes. Then Abhay's follow-up answer is split block across multiple reducers. That is make it fast. That is not the role of multiple reducers. Bishwa's answer is this. Brilliant. Very great answers. Okay. All right. Midley's question is we can. Yes, that's a question we need to answer. That's a question we need to answer, and that's a very important question. So, okay. So there is another question from Yashwant. Yashwant's question is number of input splits determine number of mapper instances. Is there something similar for determining reducer counts? The reducer counts are set by you. So we will discuss how many number of reducers you generally have to set. Okay, there is no concrete answer. There are only the strategies and there are only the upper and lower bounds. We will talk about this. Okay, we'll talk about it. We have a dedicated. Yes. All right, Yashwant, was that your question, right? Question from Mamta is there a limit on number of reducers? Number of reducers, Hadoop does not impose number of reducers as such, but but You should not create more reducers uh, than maybe twice the number of tasks that are possible over the cluster. Okay, so generally at one time, if you have more number of reducers than the unique keys, okay, then it doesn't make sense. Second, number of reduced tasks, if they go beyond the total number of machines you have, then basically total number of processors you have, then basically some of the tasks will have to wait for others to finish. So there won't be a great parallelism. All right, this is the only thing. Say one computer has got two processors, I mean dual core, other one has got four. So the total number of parallel tasks that you can execute is 4 plus 2. That is 6 tasks. If you go to say 7 reduced tasks, so what will happen is these tasks, some of them will be waiting for others to finish. Okay, so that way. So that's kind of a limitation. All right. Any other questions before we start? We want to uh, upgrade our script to do some more things. All right. All right. So here we are. Okay. So next is that. All right. So this the script which we did earlier, the MapReduce commands, they had something wrong. One problem was that the special characters were hurting us. Second, the output was not in sorted order. So let's try to solve the first thing. Okay. So what we are going to do is we are going to chain sed command. So whatever is the so what exactly are we doing here now? Okay, let me explain to you in parts. Okay, this command has got three parts to it. First part, second part, and third part. Okay, what does it do? What does it do? What does this command do? This command is replacing replacing many replacing at least replacing spaces or tabs with a single new line. Okay, so rather than only replacing space, now we are replacing space or tab, that too many times. Okay, if there are many spaces, it will replace all of them with a single new line. Now you can test this very quickly. Okay, you can test this very quickly. Let me go to CloudX Lab. Okay, and you could test it very quickly. So here I'm saying space, 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 tab, 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 and then I'm typing this. So you can see that. Okay, this is I'm putting many spaces and then tabs after tab. You can see that it is replaced tabs or spaces with a single new line. Do you see that? Okay. Next is, so if you are trying to test it out, I missed out telling you a few things. To get out of this, to get out of this command, this is taking input from standard input, from me, from my keyboard. Okay. If you are, if you start piping the data to SED, it will consider that as an input. Okay, if you want to get out of this, all you have to do is press Control D. Control D means end of the input. All right, so that's what the first command does. Now the second command, what it does is it replaces here. How many of you have gone through my regular expression session so far? Nobody? Yeah. So this one replaces anything which is non-alphanumeric with nothing. It just deletes those characters. Let's check whether it works or not. Or not. Okay. Let's say this. Or we say echo a hash hash b, and then we pipe echo to this. You can see that it replaced echo. What echo does is whatever argument you provide to echo, it just prints it on the screen. Now, instead of screen, the moment you put the pipe between the two commands, it starts sending that data to that particular command. Now, using this, we easily clean it. All right, all right. So some of you have gone through the reg section. Good, Mithili, Yashwant, and Mamta. Good. All right. So I hope these regular expressions are very clear to you. It means not. If it is in square bracket, it means not. A to Z and capital A to capital Z and 0 to 9. Okay, you can see that. All right. Now, third part is TR. What does TR do? TR translates the casing of the characters. So, for example, here we are saying convert this into lowercase. Okay, we are saying AZ and we are piping it to TR. So it has converted that to lowercase. All right. So we did three things here. Removed non-alphanumeric characters, then then translated everything into lowercase, and third thing is we replaced space and tab with a new line. Okay? So here we go. Ideally, we should use this first and then we should use rest. Okay? Why? Because it reduces number of characters. All right? So if I pipe all of them together, it will actually clean the data really well. Okay? So let's try to see if I already have one file here. If it's not, then you can do nano mycmd.sh. Okay, nano is the editor using which you can write program inside Unix. Okay, I have written. Now I'll press Ctrl X and Y. It has written this. Now this file mycmd.sh, we need to change its mode to executable. This is a very important step. We all forget this part. Make this program executable. Otherwise, if you try to run it, it will give permission error saying cannot execute this. Okay, so we created a file and we made it executable. All right. Next is we want to say to Hadoop that hey, this time I want these many reduce tasks. Okay, and this is my input data and this is my output data folder and this is the mapper, this is the mapper file, and this is my reducer. Now, since this mycmd.sh is not existing anywhere in the cluster, in earlier sed command, tr command, and all those commands were already existing in the network. So we never needed to install those. But here in this case, mycmd.sh is something which we just created. How will every node know where is this file? Therefore, you have to explicitly mention that there is a file called mycmd.sh in my bundle. So this particular file will be bundled together in the MapReduce and will be sent to the reduce, and it will try to. So it mycmd.sh will be sent to all the nodes before MapReduce process starts. Okay, this is called distributed cache. So basically, if you have multiple machines in the network, and they all are running for Hadoop, and you say that this is my file, which means Hadoop will have to take this from your local machine and send it to every node and copy it everywhere. And while executing, when you say execute this, it'll execute your file from the local place, and that place is called distributed cache. So distributed cache is a way to distribute data across the cluster. A small section of the data or a small section of files which you want to send it to all the nodes. We want to make that particular file available to all the nodes without putting that into HDFS. Okay, without putting that into HDFS, if we want to put some small data to all the nodes, we use distributed cache. Okay, so this file minus file mycmd.sh is going to put mycmd.sh into the distributed cache on each node. All right, let's try to execute this. If it gives an error, we will try to rectify it. Okay, let's see if this command is right. We just have to make it in a single line, or if we don't want to make it single line, we have to put this kind of a command, the opposite slash, like this. It says that error launching job input file does not exist. Let's try to correct that. Where is that file? Here is that file. Okay, let me just try to correct it. And ouch. All right, what is the date today? Output January 3. All right, we will go to the console and try to execute it again. And let's see what happens. All right, here you go. Hadoop fs minus ls. You can see this time we did two reducers. You can see that we got two files containing our output data. Okay, these two files contain our output. Let me just show you what is inside it. Okay, All right, you can see that now the words are far more cleaner. Now the words are far more cleaner. Okay. All right. Now those of you who wanted to sort this file by the numbers can use the Hadoop streaming in order to in order to create in order to basically, all right, let me try to do it for you. Okay, in order to sort it by the numbers, you can again pass it through Hadoop streaming process and then specify that my key is separated by space this time instead of tab. Then it will just work. All right, you can see that U has occurred 5,363 times. Okay, so we could also sort it offline without Hadoop because our output is generally smaller. And since sorting is happening based on the lexical, let's make it numerical sorting. You can see that if you want to do a reverse and check what's happening, numerical reverse. Now you can see the word called the has occurred 79,000 times, while off has occurred close to 40,000 and has occurred around lesser than 40,000 and so on. Now based on this, what can I do? That's a common question. Okay, so there are lots and lots of use cases of the word count, or so it is just one example. Word count is just one example of Hadoop MapReduce or any of these techniques which we are talking about. We are just taking one use case. There are many use cases possible. Okay. Now let me check if you have any question. Can Hadoop streaming be executed via a scheduler? Hey, sorry for this, but let me just put it here. Can Hadoop streaming be executed via a scheduler? Yes, of course. Earlier, we used to use Azkaban scheduler. Now it's Uzi that we use. Okay, I've used both of them, Uzi as well as Azkaban. Okay, so I find Uzi little better, just a little too time consuming. All right, so great, great. So is it clear to everybody that how did we clean our data and how did we? So we cleaned our data using most of the Unix command rather than coding a lot. All right. Any questions at this point? We have a question from Mahesh. So Mahesh's question is, how often you have used Unix commands versus Java MapReduce in life? So I use Unix command quite often, while Java MapReduce is very rare, and it's only on the occasions when the data grows beyond, say, 2 3 gigabytes. Okay, so only in those cases I have used MapReduce. But again, in the MapReduce itself, I've used, mostly I like to do the Hadoop MapReduce with streaming, Hadoop streaming. Okay, and there again, the mostly it's a Unix command, but sometimes Python also I've used. Okay, I don't have exact count, but yeah, the ratio of doing it through Unix command lines is very high, because generally these are chores, as in quickly getting things done. Instead of, these are not like building constructions. Okay, therefore I generally go with my Unix command either directly or via Hadoop streaming. All right. How do we get two reducers on the previous example? How did we get two reducers? Yes, yeah. Oh, that I forgot to mention. All right, you see this? In this command, we have mentioned -d maprad dot reduce dot tasks. Okay, we said two. Okay, and therefore, if you see, part 0 and part 1 were there. There were two files. There were two files. You can see that there were two files in this folder. You can see that these are two files, part 0 and part 1. All right, like this. So if we, so this file goes to HDFS and the other file also goes to HDFS. Yashwant is saying that isn't it often that data will be more than 3 gigabytes? So mostly what happens is that when you have raw data and you churn it for the first time, you get the clean data. And the clean data is generally far smaller than the raw data. And mostly in the life of a data scientist, you, in a normal life, you generally don't cross more than 10 gigabytes of data. All right. So Yashwant's question is, why doesn't, no, there's no such thing called it doesn't handle. It's just a matter of practice. So I was saying that one is, we could do everything using Unix command line, just the way we did a sorting just now while we were doing here. I'll show this part here. What we did here was we sorted the data offline, right? We sorted the data offline. And when you try to sort the data offline, what happened offline as in non-Hadoop? We sorted this data on the local node. So this work is not distributed, and after a point of time, the RAM will take a toll and it will be very slow. We are going back to our original discussion. Why do we need big data? So when I was comparing the two approaches, one using Unix commands in the normal way, and other is using streaming in a in a production environment. So using Hadoop streaming, using MapReduce via Hadoop stream. We do that when the data size grows high. Okay. Otherwise, we generally go on with mostly the Unix commands. If Unix command do not suffice technically, then we go with maybe Python. Okay, because with Unix commands, getting everything done is very difficult. Okay, so I was comparing offline versus on Hadoop. All right, does it make sense to you? So Okay, good question. All right. The other question is, in the command line, we have not specified how to split the keys for each reducer. By default, it splits based on the hash code. Okay. Every string has got a hash code. If you are from any programming background, every library provides a way to translate a string into a number, and that strategy is generally called hash code. So we generate a numeric value out of out of the out of the string, and then it basically divides the hash code by total number of reducers you have. It divides the hash code by total number of reducers, and based on the remainder, it puts that particular key on the node referring to the remainder. Let's say you have two nodes. In those cases, what it will decide is, let's put even on one node and odd on another, even hash code. Okay, for each key it will compute the hash code, and if the hash code is even, then it puts it on first one. Then if it's odd, then puts it on second one. If you have three nodes, what it will do is, the numbers which are multiples of 3 goes to the third one, the one. So it will basically divide it by 3, and whatever is the remainder, it will send that uh, output to that particular node. Okay, let's take a case of 4. If that let's say you have got 3 nodes. Okay, I'll just okay, let's say hash code is 4 and you have 3 reducers. Okay, so it'll do hash code of some string is 4, so it'll do is 4 percentage 3. What is that? 4 percentage 3 is 1. So it will go to third second reducer. Okay, so if it is 0, it goes to first reducer. If it is 1, it goes to second reducer. If it 2, it goes to third reducer. Okay, similarly, if hash code of a key is 30, so 30 percentage 3 is 0, and hence it goes to first reducer. Okay, if hash code is say 41, so what happens is 41 divided by 3, what is the outcome? 2, right? Percentage means remainder. When you divide it something by something, what is the remainder? Okay, so the first reducer, not one reducer, first reducer, this will go to third reducer. All right. Question from Yashwant is, what will be the hash code for ABC and CBA? Okay, you will have to find it out. Okay, if you are from Java background, then you can quickly compute the hash code. Okay, All right. Any other questions at this point? All right. So that was mostly about Hadoop streaming. There are a few more questions. Okay. Keep the questions coming and hear the questions correctly. In case I'm not speaking correctly, the question, please stop me and ask to repeat the question. Okay. All right. Okay. Next question from Biswa is the command file you created has sed command? Yes. So what did our command file has? Let's have a look. Okay. Nano, nano, and we had, you can see that. All right. Good, good. Biswa is asking, and the jar tells about the input file. Yes. So when we say Hadoop jar, this thing, the Hadoop command uh, gives all the argument to the MapReduce program, and from there it goes. So now is the time to move ahead to more Java MapReduce. Okay. So we will go back to what we were doing. All right. Yeah. Okay. All right. So it's okay to have no reducer. In one of the examples which I gave you, where somebody asked me about grep. Somebody asked me about a real life example. So I was showing you how to grep error messages across so many files. So in there, we did not have a reducer. Okay, we did not have a reducer, we only had a mapper. The number of files in the output were decided based on how many number of mappers are there. Okay, so it's okay to have no reducer, right? For example, here you can see that we may choose not to have any reducer at all. All right, and this reducer, if you can use, without a reducer you can generate a file of this word count itself. You can generate it sorted by the numerical value, number of counts. Okay, without a further reducer. Okay, you don't need a reducer there. It's okay not to have a reducer. Generally, if you don't have a reducer, the but output will be sorted, but the there will be no reducer side logic. There will be nothing happening on the reducer side. It'll just take whatever mapper is giving out, it will sort it and then save it onto the disk. Okay, and if you do not want any sorting, then you can say explicitly saying mapper at reduce task equals to 0, and there will be no sorting at all. In this case, if there is no sorting, meaning there is no shuffling happening, there is no heavy lifting. Okay, there is no heavy lifting such as sorting, and in that case the mapper will decide how many number of output files are there. Okay, when there is no sorting happening, number of maps this is another question which people ask most often. How many number of mappers are generally executed? It is a function of number of files. Sorry, number of blocks of a file. Okay. Also, sometimes even though your data is small, but you are doing a very heavy lifting. Imagine that you are writing a distributed crawler. What is a distributed crawler? A tool which will download thousands or hundreds of thousands of websites parallelly, right? You want to distribute this kind of work, so you will put the URLs in a file that becomes your input data and then execute it on the cluster. So what happens in this case is, so if you have, all right, so you are writing a distributed crawler, and what you did was you wrote all the URLs in a single file and fed to the mapper task, and your mapper task is all it does is for each input line it downloads or wgets, wget or curl or any other tool which basically picks up one each URL from the input file and start downloading. Now you can guess that even for $100,000, so even for 100,000 uh, URLs, even for 100,000 URLs in the input file size will be hardly few hundred KB or maybe a few MBs, megabytes. Effectively, even though your input file is having single input split, you may want to have more mappers, right? Even though your input file contains a very small data, still you want to run your mappers on more than one node. In those cases, you may want to set number of mappers by using conf.set number of map task in case of your Java task, and minus d mapread map task in your Python in your streaming. This first question is, all right, here in this first question is, why do we need to specify why do we need to specify mycmd.sh twice? In one, it's a program. In other, it's a file. I'll explain to you why. Maybe if this mycmd.sh is expecting some command line argument such as xyz or 1, right? So this is your mapper. This command is your mapper, while this part tells that before we run this command, we need this to be copied to the same node. Okay. Now imagine that my cmd.sh is calling mylib.sh. Okay. My cmd.sh is calling internally. Let's imagine that inside my cmd.sh, the first line is call mylib.sh. Now here mylib.sh is not a mapper, but mylib.sh is important function which mycmd.sh is using. In those cases, you will have to say mylib.sh like this. Okay. So one part, the minus file part is take this, install on every node before running my code. And as soon as you finish running a code, it just deletes the distributed cache. Okay? Because these my cmd.sh, they will be kept in a local distributed cache where the actual execution will happen. Okay? From where the actual execution will happen, and then as soon as it finishes the MapReduce task, it will delete all of the cache data. Great set of questions. All right. Now, the main question, which most of you have been asking, that main question is, who decides number of reduces? Okay. Who decides number of reduces? The answer is that there is no finite answer. Okay. There's only a range. There's only a range. So the range is, it starts from 0.95 to 1.75 times the maximum task. So every cluster has got maximum number of tasks that they can execute. Imagine that you have code to do a processor on one, which means it has 4 cores. That means, and you have configured your Hadoop that okay, you can execute 4 parallel tasks at the same time. Okay, so if you sum up all such maximum number of tasks each node can execute, then the total the total that comes out is the max task your Hadoop can execute. Okay, so max task is equal to number of nodes into map reduce tasks that can be executed simultaneously per task tracker. Okay, so this formula may be wrong if your all nodes do not have the same number of cores. Okay, if some of the nodes are having 2 cores, other are having 1 core, and fourth one is having even more, then this formula may not work. This is good for the uniform one. In that case, if the machines, if the task trackers have different configuration, in those cases you sum up, you count how many tasks your cluster can execute per second, okay, parallelly. So, based on that, you get the maximum task on the cluster. So, your number of reducers vary somewhere between 0.95 times 1.75. Also note that your cluster may not be able to execute all the tasks parallelly. Okay, but it may not be able to execute all the tasks parallelly, but it will queue them so that once some task finish, other take it up and do the work. All right. So your number of reducers are generally a function of maximum task that can be executed, and number of reducers are generally proportional to 0.95 to 1.75 times maximum task that can be executed. Okay. So, and on each node, if you want to increase number of tasks that each node can execute, you can increase it. By default, it's a 2 tasks per processor. Okay. Now, what is the downside of having so many reducers? If there are more number of reducers, there will be more transport of data, there will be more shuffling, okay, and there will be more framework load, okay, and but good news about more number of reducers is that if something fails, okay, it wouldn't be having so much of contribution overall. If one of the reducers fail, it will be just that particular loss, and that can be sent to somebody else. Okay, so that's the only those are the benefits of having. I'll show you this again. So if you see this diagram here, it shows that if there are two, if there is only one, yeah, if there is only one reducer, how many transports are happening? One, two, three, right? But if you have two reducers, the total number of transports that are happening is one, two, three, four, five, six. So total number of data transport is happening around six times. Is it clear? Earlier it was only 3, now it's 6. What if What if you have three reducers? How many total number of transport that will happen if you have three reducers? Anybody? Okay, so correct. It's 9. That's right. It's 9 times. It won't be a factorial. It will be multiplication of total number of mappers by total number of reducers. Okay, good. Now, there are very interesting question from Mahesh. So map does not put output in HDFS. So there is a risk of data loss. Yes, there is a risk of data loss. So all it does is, in case any of the tasks fail, the output generated by that task is completely disregarded and the same task is given to somebody else. And that's one of the reasons if you have too many maps, it's quite useful. And similarly, if you have too many reducers, it's sometimes quite useful because it's going to give a good resilience in the sense that if something is failed, if something has failed and we are scheduling that work to somebody else, it is only small data that has failed. Correct? Therefore, sometimes the having many reducers does actually help. Okay. Now, question from Mahesh, follow-up question from Mahesh is, I get that, but what if I want to preserve the data for later use? Okay, why would you want to preserve that semi-prepared data? Instead, you write your MapReduce job, which will prepare some output, and keep that, preserve that. Okay, preserve that. In case you want to preserve the data for further use, don't have a reducer. Let mapper write the data directly into HDFS. If you do not have, if you do not have a reducer, the output of mapper is going to go in the HDFS. So your need will be fulfilled there. Make sense to you now? All right. So there is a very good set of questions. First is, if I want to preserve the data of map for further use, that we can use by removing the reducer. Other way is we can directly interact with HDFS. Okay, there's a library which we'll talk during our Java session, that there's a library which will copy, which using which you can do the file IO at this point of time. Okay, there is a file IO library using which you can read or write directly to HDFS. Okay, from anywhere. Good. Now there is a very interesting question from Mahesh. The question is map function does work like downloading files too and other tasks? Yes, it does. It does. Okay, because if you imagine if you imagine a tool called Scoop. Okay, let's take a case of tool called Scoop. What does Scoop do? Scoop brings data from various databases to Hadoop. Okay, now while you execute scoop, it's going to connect to database, not it's not going to talk to HDFS. It doesn't have the input data which is lying in the HDFS. If you use scoop to copy the data from normal database to this, right? So scoop doesn't have any HDFS file, no blocks, nothing on which it has to operate. Now, in case of scoop, there is anyway lot of hard work that is required to pull the data from databases and then write to HDFS. Okay, in those cases, in those cases, being able to read database is quite useful. Also, since we can tweak map functions that hey, even if there is a small data, please have these many please have these many mappers. Okay, even if there is no input split. All right, so that's about it. Did it make sense to you? All right, good. I'm happy that I was able to convey. All right, now let's discuss these things which are pending since last week. Okay, so for computing frequencies of letters, do you need MapReduce? Anybody? Anybody? Okay, so when somebody asks you this kind of question, when somebody says this kind of question to you, it's a very common phenomena. If you are not from data structure kind of background, have a look at a book like Programming Pearls by John Bentley. Okay, so whenever people ask you this kind of question during interview or any data related question, your question generally your instead of answering it without anything, you just instead of answering it, you ask many follow-up questions. Those follow-up questions are that hey, how much is this data, how much is this data, and what kind of data is this? Okay, that will give you a lot of clear insights into the problem. So the frequencies of, I mean, as a matter of fact, when we interviewed at Amazon or earlier at Disha, we paid a very close attention to the questions being asked by the candidate, and that's a very important. We had some questions when we had some rounds, technical rounds, whereby we would observe, we would try to throw a question and observe whether the candidate is asking the right question. Okay, so in the same spirit, you should generally ask, you should generally ask that hey, how big is this data, before taking a call whether to go with MapReduce or go with the normal single node system. Okay, so now what do you have now, can you ask the right question? Anyone? So it would matter that how much is this data, based on that whether we need MapReduce or not. Okay, so without MapReduce approach, you can create an integer array of 26 size, scan the text character by character, increase A0 for A or A25 for Z, okay, and others in between. So it's a rudimentary, very simple approach, correct? It's a rudimentary, very simple approach. All we are doing is we are maintaining an array of 26 size. Okay, we are maintaining an array of 26 size, And as and when we encounter small a, we increase the a0. As and when we encounter z, then we increase a 26th, 25th. Okay, and everything in between them. So basically, if the data is very small, this technique is good. But if the data is going into GBs, then these techniques may not help much. All right. Yes, that's the question I was expecting, Biswa. All right. So this is a plain text file. All right. And this data, let's say the data is of 6 GB. Now, what will be difference in the approach if the data is around 6 gigabyte? Anyone? In that case, if the data grows to beyond 5 6 GBs, then you go with MapReduce. Okay, is it clear to everyone? All right. So in case of MapReduce, this is the approach I would follow. Okay, so whatever we did in case of the MapReduce, non-MapReduce approach, where we just counted number of characters, now we can do that as part of Mapper. Now we can do that as part of Mapper per line at a time. Okay, all right. Now second question is find anagram. So is this clear to you? Yeah, is this approach clear to you, everyone? Anyone? All right. Now moving to, okay. So who has finished this one? Anyone? I think Yashwant has done, but others have also done, but they have, you have not. Yeah, you just inform me once you finish your subjective question so that I can quickly evaluate. Anyone? Abhay, Biswa, Lakshmi, Mahesh, Mamta, Medli, Yashwant. All right. Okay, so please spend a little bit more time to solve these problems. Let me try to explain my approaches. So my approaches are not final. Those are not the only approach. I remember in last one of the sessions, one of the candidate actually came up with a very good answer. So I like that approach as well. Okay, so my approaches are not final. So you can actually come up with a better approach. Okay, Mahesh says that he has used each string as the key and the value. What happens in case the hash code collides? Second, the hash code will not guarantee that the two strings, one, two strings, one which is an anagram of another, will have the same hash code. Okay, do you think that two anagrams will have the same hash code? No, right? So what he has done is he has used a hash map, convert each character to ASCII values. Now, but then what he's saying is if you sum up, very good approach, but there are catches in that. So if you think about it, so what is the objective? Let me reiterate. Objective is find the anagrams in a huge text. And this huge text might contain billions of words. Okay? And what does it mean by anagram? If you rearrange the letter of one word, it becomes anagram. So there could be many anagrams of the same word. Okay? So all we have to do is we have to find out who is anagram of who in this big text file. All right? Now, how do you do this? So one of the approaches, what he's suggesting, Mahesh is suggesting is he has uh, prepared key as hash code, which is sum of all characters, all chars ASCII value. Anybody? Anybody? Can anybody question it? Yes. Do you think it is correct or wrong? All right. Yes. Yes, Abhay, I saw that, and that your approach is also correct. As Yashwant, I will not tell the approach to everyone right now. Okay, so can anybody? So what he's saying is, so the cat sum will be same as act. Okay. Now my question is, can anybody question it? Can anybody? Okay, that's very good. So Mahesh, the Biswa's question to you is capital letters will have different ASCII values. That's correct. Anything else? Okay. So in a response to that, Mahesh is saying that I converted to lowercase. Okay. And any other problem do you see? So what he did was like if you remember that there used to be a game, we sum up the values of each character, and then whatever comes out, that it becomes the number, and that number is the key. So is this okay? Do you think this approach is correct to find the anagrams? Actually, no. ACT, now imagine the hash code of ACT and and BBT is will be same, right? So the ASCII value of A is 1 lesser than B, and ASCII value of C is 1 greater than B. How will they be different? So in your approach, so are you reusing the hash code or are you using this? Are you using summation of the ASCII values? Yes, thank you, Mamta. Thank you, Mamta. Mamta also has the same point as what I'm saying. Okay, and Biswa is saying, what if there is a digit that will sum up to another combination, billion? There could be another kind of things like a. There could be many such combinations which will have the same ASCII value. I can give you at least 50. All right. Yes. So that approach is nullified. Do you think of any other approach? Brilliant. Brilliant. Now, moving ahead. So, yes, this is what I'm going to do. For each word, what I'm going to generate is the key will be the unshuffled words. Okay, so what I do is take take a word, arrange the letters such that the letters are in increasing order. Letters are in increasing order, correct? Which means that all the anagrams will generate the same arrangement. All the letters, all the words which are anagrams of each other will generate the same sorted word. So, for example, we took the, the smallest letter out of the is E, and then H, and then T. So, E, H, T will be the key. Now, you can see that all the anagrams of the are going to have same key, isn't it? Similarly, for cat, whether is so cat A is smallest, then C, then D, T. I'm going alphabetically. So the cat will generate act as the key, while act will also generate act as the key, and tack will also generate the act as the key. Now you can see that all the anagrams are generating the same key. Which means when Hadoop does the shuffling, Hadoop does the grouping, all these values are going to come together. And in the reduce phase, we can easily say that this is the anagram of these, or these are the words which are anagrams of each other, because Hadoop will group all of the words. Yes, makes sense to you? Is it clear? Is this approach clear to everyone? Yeah? Good. So that was anagrams problem. The third one is comparatively simpler. Yeah, Mahesh has some question. Okay, he's saying yes. All right. The third A is simpler question. A file contains the DNA sequence of people. Find all the people who have same DNA. I think this one everyone but everybody must have done. Yeah. Abhay, Bishwa, Lakshmi, Mahesh, Mamta, Midli, Yashwant. Yeah. All right. So who has solved this one? Abhay, Bishwa, Lakshmi, Mahesh, Mamta, Midli, Yashwant, Mahesh, G. Okay, so do attempt these problems. The other problem, third one is that a file contains DNA sequence. So how did you solve it? This one is very easy. All you have to do is make the DNA as the key and user ID as the value, which means all the people whose key is same, whose DNA is same, they will be accumulated together. All right. Now the next one is little more tricky. Find all the people. Okay, so this one is clear to everyone, right? This diagram, the previous diagram, I think we'll revisit the new one. So the all right, so third B is little more trickier. I haven't seen any of you. Abhay, have you solved it? All right. So there is a file that contains DNA sequences of people. You have to find out that who are the people whose DNA is either identical or the mirror image of each other. Okay. What does it mean by mirror image? You can see that user 1 and user 2 have exactly reverse DNA, ACGT, and from this is from left to right, and from right to left it is ACGT. So user 1 and user 2 are mirror image of each other. You have to bring, and there are a billion entries like this in this file. So there are a billion entries like this in this file, and you have to write code so that you can bring them together. Okay? You have to bring them together. Okay? So, Abhay, will it be possible for you to copy paste the approach? Okay, I'll go through your approach. No worries, I'll go through your approach. All right. Now, how do you bring these people together whose DNA is either same, meaning identical, or either reverse? So, basically, the whole agenda is find a common key. Find a common key so that all such people who you want to bring together, they have the same key. If they have the same key, then automatically Hadoop will bring together. Hadoop will bring all such people together if you are able to figure out what is that key. Okay? Now here we have to keep a key which will be same for all the users. All the users having this particular property. Okay, now what do you do in this? Okay, here, so what you do is you take the DNA of a person, you reverse it, you reverse the DNA of the person, then compare the original DNA and this reversed DNA, and whichever is the smaller you pick it. So effectively, where all the people whose mirror image whose DNA is either mirror or the same will always have the same key. Okay, will always have the same key. The smaller of the DNA and its reverse is always going to be same. Whether it's reverse, we compare the reverse to the DNA or DNA to the reverse, the smaller will always be the same. Therefore, we will get we will get a good we will be able to bring all these users together. So from here you can see the who is smaller than ACGT and TGCA. Quickly, who is smaller than AC out of ACGT and TGCA? ACGT, brilliant. Okay, and who is smaller of TGCA and ACGT? Correct. Now ACG, what is the mirror image of ACG? What is the mirror image of ACG? GCA. So out of ACG and GCA, who is smaller? Correct, ACG. So user 3 will have a key called ACG. Now user 4, what will be the key for ACGT? Sorry, how do I go back? Yeah. All right. And that's, so I think it's clear to everyone. Is it clear to everyone now? But if you see user 7, even though it's an anagram of user 1, it will not be in the same family as user 1. Okay, because what is the opposite of tcga? It will be agct, right? And smaller of tcga and agct is agct, correct? And that'll be the key in case of user 7. All right, so that's how you can bring such kind of users together. All right, so it takes a bit of time to figure out how can you convert your problem into this sorting problem, or how can you convert this your problem into MapReduce. It takes a little bit time. It took me a fair amount of time, and this question which I'm asking you right now, this DNA question, only few people have been able to solve it, even in my interviews when I used to conduct interviews for various people. Yeah, so basically it takes a little bit of time to getting used to the MapReduce kind of psyche, how to convert the problem into the normal memory hog, as in most of us try to solve most of our problem using a hash map or hash table. All right, and these kind of problems can be you have to get out of that habit of using hash table or hash map, because hash map is inherently memory intensive, because everything has to be kept in the memory in order to handle such kind of uh, in order to solve your problem. Therefore, the hash map kind of solutions do not generally work. Or dictionary, we call them dictionary in case of Python, and hash map in case of Java or C sharp. And so those things do not really scale well, and thereby you need to figure out how can you break down your problem into a sorting problem, into how can you utilize sorting to solve your problem. All right, so that is one. All right, this fourth problem we'll discuss in the next session. All right, and then we'll continue with our Java MapReduce. All right, so try to solve these problems whatever we discussed today using Hadoop streaming. Use Hadoop streaming to solve today's problems, to solve these four problems. All right, thank you very much, have a great day, and I think all right, bye bye, have a great day.